talking about something that has become somewhat of a buzzword in the AI world, real-time interactions and recommendations. And we're going to really be getting down to the nitty-gritty of what real-time really means in this context, because something we've picked up by being in the industry is that people's understanding of real-time is very different, and understanding of instantaneous interactions is very different. So I'm going to start by kicking off on something that's more on the philosophical side, because I think before we start talking about real time, we need to first talk about time itself. Although time is something that dictates our realities completely, it is inherently a concept that we created. It is something that is subjective in how it is experienced. I think most of you would be familiar with people saying it seems like time is speeding up, which is scientifically impossible, but it just points to the fact that it is subjective, and time is measured in our minds by a rate of change in our environment. So if many things are happening at the same time, it might feel like time is moving more quickly, whereas if you're sitting watching grass grow, it moves a lot slower. So time is very much reliant on human experience. For us to understand how our customers are experiencing time and what they expect from time, we have to understand the context they live in. And what that context is at the moment is one of extreme technological advancement, where rate of change has just completely exploded, and the things that people are exposed to within an hour is completely different to what they were exposed to within an hour 100 years ago. And this completely changes how people value a second versus how they valued a second decades ago, and also changes what they expect within a second or within a millisecond, but we'll get to that later. So when I was making this presentation, I used artificial intelligence, but that got me thinking about the very process of work and how that's changed with technological advancement, and how that actually changes how people perceive time and their lives. If you're living a busy life and there's a lot expected from you in a short space of time, it raises your expectations for other people to meet you instantaneously as well, because you're expected to deliver a lot instantaneously. If you think about the process of writing a letter, a well-written, thought-out letter, handwritten, would take an hour. When the typewriter came along, you could maybe write 2 or 3 pages. When the computer came along and you had access to the internet, you didn't have to externally source research. It would take a lot quicker. And now we have artificial intelligence that does the work for us. So what is expected of people to achieve within an hour is a lot higher than it was before. And that also means that there's a lot more expected from businesses, because people value shorter spaces of time a lot more than they used to. Why does real time really matter to businesses? I think this is a good segue. Shorter spaces of time matter more to people. So businesses need to care about meeting people in those moments. We're going to be talking a bit about how seconds are not necessarily the conversation anymore. It's more about milliseconds. We did some research to back up what we were saying, because we were throwing it around a lot that milliseconds make a difference. I think it is worth showing that it really does make a difference. So these are 2 separate studies from 2 different industries. One is e-commerce and the other was from finance and banking. The first one showed that 100 millisecond load time delay on a website reduced conversion rates by 7%. And the other one showed that 100 millisecond faster load time led to an 8.4% increase in conversion rate. So very similar results there. And I think it just speaks to the fact that, it gets down to 100 milliseconds is 0.1 of a second. For it to have such a significant increase, 7%, 8.4% maybe doesn't sound that significant, but it's 0.1 of a second. So it really does come down to milliseconds. I'm going to hand over to Bodhi now to speak more about how milliseconds matter. He's going to take us through a bit of the ecosystems.ai architecture as well. Over to you, Bodhi.
Thanks, Nicola. Just to address something you said earlier, to honest like my physicist roots, you can go forward in time according to a relativistic understanding. You just can't go backwards. So that's something I need to get off my chest. Back to real time. This is another set of stats that we found while we were researching this point of discussion. Please, if you have any questions, speak up. A lot of this is meant to spark some discussion around that. This is another interesting stat we found. It was a study by Google in 2018 across 900,000 or nearly 1 million sites, and it showed a change in bounce probability according to like artificial load time, like change in load time. So as we can see, a change from 1 to 3 seconds in load time increased the probability of a customer bouncing by 32%. This data, along with the ones we were chatting about earlier, really speaks to a certain approach that we have taken to real time itself. So I feel like there's two ways that you can understand it. One is this sort of more research concrete way where you do some empirical A/B testing and you pick up some stats and you crunch some numbers. As we've shown, you can see quite a meaningful difference. I mean, 8% conversion is quite a huge margin, right? So we can see real empirical repercussions of, as Nicholas says, meeting your customers in real time in the moment that it means the most to them, right? There's another half to it which may have brought a lot of people here to the discussion, and that's the intuitive side of real time. It makes sense that if you make conversion as easy as possible, so you make the time you have to wait to convert as little as possible in this instance, then you're gonna see an increased rate of conversion, right? That makes intuitive sense to us. We have a question from Francois. Let's see what it is. Francois, in reference to your question, I'm going to unpack it a bit more in a second when I speak about what the phrase real time actually means, especially to like us at ecosystem. So this specific study measured in the order of magnitude of seconds. So the ones we were talking about earlier was that like handful of milliseconds change in load time. So that's impacting like actual conversions. So actual products bought, actual money in the bank. Whereas these bounce probabilities that we're talking about is just the probability of someone giving up. But the reason why they're so different and why we see much higher numbers here is because we're talking about a much broader period of time. We're not talking about milliseconds, we're talking about seconds. And also because we're talking about a much more low committal activity, right? Just staying on a page is a much lower commitment than buying something. So that's why we see quite a big difference in the stats that we've shown here, why we're seeing single digits and milliseconds versus double digits and seconds. I hope that explains and gets rid of some of that confusion around that. We just wanted to show the two sides of the coin. And I think that links to what real time means to us. Nicola, maybe if you can go forward a slide. When we speak about real time in the context of AI, we're talking about delivering AI intelligence to another firm, a business, right? And we talk about how we should achieve that. This comes with what we have under the first heading here, minimizing operational costs. As we can see, a great delay in delivering analytics or recommendations, predictions, or next best actions, any delay in the delivery of that is like operational cost. It's costing you money, as we've seen, literally in the order of magnitude of milliseconds. For us, the phrase real time doesn't necessarily refer to just milliseconds. It refers to what is like, how can we provide this service essentially in such a way that minimizes the amount of time required to deliver it to the customer. If you're doing a more complex calculation, you're gonna expect to see the time associated with delivering that prediction go up. We can't always live in the 5 millisecond wheelhouse of like the ideal world. Like sometimes some of the things we want to do on the back end to like reach a certain level of sophistication in our analytics and in our predictions requires time. That's just part of the trade-off. But real time doesn't necessarily mean a specific threshold of time. It doesn't mean sub 500 milliseconds, your service is real time. We're talking about how can we approach that service in such a way that we minimize the time, given the current physical constraints of our universe and of the technology and on the infrastructure it's running, etc. How can we minimize the time required to provide that service?
When you talk about how certain things might take a little longer than others, it reminded me of the fact that time is inherently contextual, and the way that your customers will expect you to act in a certain context will also determine whether you make use of real-time capabilities. For example, if a customer is asking for in-depth reports on their spending and advice on budgeting, an instantaneous response might give rise to some suspicion, and some things are better to take longer. Whereas if you are typing in responses to a USSD prompt, you want an instant response. And if you don't get it within milliseconds, you opt out, or with web page load time as well. So it is highly reliant on context and people's expectations.
Thank you. That's a great point. It links to that whole idea of real time more as an approach rather than a specific number or threshold. Thank you, Nicola. Maybe actually go back one slide. There's still one thing I want to speak to. It's a little bit tangential, but it kind of goes hand in hand, especially at ecosystem, is the idea of permanently in production. So this is kind of the other side of the coin for us in terms of minimizing operational costs in the delivery of AI analytics, right? And that's it is kind of, as I say, the other half of real time, because downtime itself is the worst possible form of latency. In some given time frame, you literally need to block out a certain amount where you can't make sales and you can't make money, which in our world is losing money. So permanently in production is another thing that has motivated the architecture that we're going to speak about in a moment. So yeah, it's being able to deliver in real time and stay permanently in production, which is the idea of having near zero downtime in how you manage the system and deliver the analytic. Yeah, and then of course, our second point here is maximizing ROI. This speaks to what Nicola was saying in terms of you need to align your real-time capabilities with your business goals. So if in the analogy Nicola was speaking about, like financial advice, you need to align the desired business goal of delivering profitable financial advice with real-time capability. So that speaks to what Nicola was saying. And then that third point sums up everything we've been speaking about, making time to respond as instantaneous as possible in a given context. So the next thing I specifically want to talk about with you guys is, now that we've covered a little bit of theoretical ground in terms of what real-time sort of means to us, why it's useful, we know that it has real business impact. So then how does one achieve real time, and how is our real time philosophy reflected in the product? In my mind, the easiest and most visual way to show that to you is in the actual architecture of how the product is designed, that the real time capability sits. It's in the making of every decision within R&D, deciding how is this going to impact the latency of delivering the analytic. So to go in a little bit more detail, the ecosystem platform itself and how it achieves this is via what I describe as a network of containerized environments. Essentially, it's just a network of connected environments, each responsible for executing some set of tasks and doing some amount of work together through communication, essentially REST APIs, that then operate as a sophisticated AI analytics platform. That's what we mean when we also often throw out the term worker architecture. We mean that the structure of the platform is in such a way that there's a bunch of self-contained environments, each responsible for some work, and together they provide the entire process of delivering our services, from dashboarding and stuff. We have dashboard workers. For example, Grafana is something we see a lot of success with and that a lot of our clients really like. So we have a Grafana worker. Whenever you spin up an instance of the platform, you're gonna essentially create a bunch of these containers that are going to be responsible for executing these tasks. Yes, Nicola?
I just want to clarify for maybe the non-techie crowd, because it took me a while to get my head around this, but containers, the reason why containerized environment enables real time is because a container contains all the things needed for a certain task to be executed. Instead of having to gather resources from different parts of the network and put them together, the container already has that all readily available, which is what makes executing these tasks more efficient. You can correct me if I'm wrong, but I just wanted to clarify.
Nope, that's a great point. Maybe just to give some distinction as to what, so like for ecosystem, like the ecosystem containers literally have their own file systems, but an important characteristic of containers is that they still ultimately communicate with the host kernel. And that may not mean a lot to a lot of people, or it may, but that's the basic defining characteristics of our containers. So we can go a little in depth into each one of their functions and how that plays into the overall picture. For example, we have right here on the left-hand side, we have the ecosystem notebooks container. This container is responsible for holding an instance of Jupyter Lab, which is, for those who don't know, it's a Python notebook platform. And you can use that instance of Jupyter Lab. It comes pre-installed with the ecosystem notebooks Python package, which allows you to interface with the rest of the platform entirely in Python through the notebooks. Another one would be the ecosystem workbench, which is our GUI, which is kind of what we call our low and no code graphical user interface. We do a lot of our demos and meetups. We work with the workbench because it's very visual. It's nice to help explain some aspects of the product. And I think after the slide, I'll give a small example of some of the latency one can expect when operating within the ecosystem platform, specifically using the workbench. That's another example of the containerized structure. And then there's the ecosystem server. This is generally kind of the central node, and it is responsible for quite a few things like the MongoDB instance, etc. That makes the world go round in regards to the ecosystem platform. But perhaps the most important one to speak about, which is past this red line. This red line typically indicates what we call in production or in deployment, right? And that's the ecosystem runtime container. This is where a lot of the magic sits in regards to how ecosystem achieves real time. This specific container build holds almost all the necessary tools are required to execute on a given configuration. Using your interfaces, it's going to be a glorified way of handing a configuration for a AI use case, whether it be some model that you've trained, or whether it be a dynamic model that is going to do some online learning, or whether it literally just be a database lookup. You're going to use that interface to hand off that configuration file to this ecosystem runtime at its given API endpoint. And then that runtime is going to load that configuration and be able to execute according to that configuration. And you can query the runtime with more API calls, passing specific parameters. And depending on what configuration you've handed it, it is going to execute and respond to that API call in a very small amount of time, because it requires very few sequential inter-container API calls to make that happen. Depending on the task, but yeah, the idea is very, very few. So obviously, in regards to database management, it's going to need to often fetch some data through the ecosystem server or etc. But 90% of the required tools sit within that environment, which allow it to respond without having to speak to the rest of the platform, if you follow me.
And I think also some of the things that you mentioned there speaks to how the real-time capabilities are kind of horizontally scalable, because the real-time capabilities are customizable because you push certain configurations to the runtimes. Can you clarify a bit about how you can horizontally scale the real-time capabilities?
Yeah, so part of one of the other benefits of the containerized architecture is that with the ecosystem runtime image, you can have whatever container engine that you're using. In this graphic, it's specifically Docker, but you can have that engine build as many of those runtimes as you need. So you can, in theory, build as many ecosystem runtimes as you have infrastructure to handle, and then you can hand each of those the same or different configurations, and then have all your front ends, wherever your API call can be coming from, they can query those runtimes indefinitely, as you can have indefinitely many runtimes, depending on how many you choose to spin up. Another important aspect is to understand from a technical point of view, what is parallelism, concurrency, and asynchronicity in order to achieve the illusion of real time. These are very lovely words. I'm familiar with a few of them. Carly, I'm not sure if I'm pronouncing your name right. If you could speak up, maybe you have something to say. Hi.
Maybe I can just jump in a bit.
Jay. Hi, Jay.
So, yes, you're right. There is an instance of execution through the threading engine that'll create the perception of reality. But we've created our own threading system that deals with the parallel execution. So there's a threading engine that knows there's a primary priority execution path that runs through the entire product with a priority that means that it is the core data collection and also the core scoring storage engine. When an API call comes in, it knows its priority, it understands what it needs to do based on the configuration provided. Let's say you got a static model. Static model means that you need to get your parameters from a data store, or you bring the parameters for the scoring through an API. You have a dependency to find that data first, prepare it into your scoring structure, score it against the model, get the results back, and pass back the results to the API in the shortest possible execution path. There's no parallelism there. There's a threading engine that deals with the threads, full load. One of our engines that run at, let's say, 5,000 to 10,000 interactions per second means that there might be 400 or 500 threads running in parallel that our engine internally manage. And we built an infrastructure to be able to handle that automatically. If you deal with certain parameters that you can set, and you want to set, explore, exploit, like a multi-arm bandit, or you want to set an offer matrix to iterate through, or any one of those are loaded in parallel. So that means they are depending on the execution path. So that means at any point in time, it will parallelize every path of execution to the point where it's needed in the platform. In our corpora configurations, if we want to load predefined corpora, there's a static and a dynamic configuration. Static means that It gets loaded up front and it's permanently available through the execution path in the core engine's memory base. So there's a shared memory and localized memory that we manage independently, especially for real-time engines. You need to do that. And then there's another type called dynamic. Dynamic means it gets updated based on a certain set of rules that you set. So let's say that you have a parameter that updates in real time from some other system, and you want that to be available the moment, a few milliseconds later in your post after you've done your scoring, and you want to influence a pricing calculation, or you want to dynamically influence, how you're going to deal with a threshold, or you want to take your cost of purchase and include it into your pricing decision, or you want to have any kind of dynamic capability, all of that becomes available. The handling of the threading, the scoring, and everything in dynamic and in static models are predefined. In dynamic models, it's slightly different because dynamic models run two major threading paths. One threading path is a back-end engine that runs continuously that you can set a time frame for. So you can set it between 1 second and almost infinity, and it will update what's called an option store. So the option store deals with normalized scores that run parallel to the main scoring engine. Depending on your use case, you can set a parameter dynamically to be at a customer level. The scoring happens in real time. The model gets trained in about 20 milliseconds. If the model is set to aggregate at a category or a contextual variable level, then you can set it from 30 seconds to maybe 5 minutes, depending on your use case. In some banking, you can set it maybe as long as 10 minutes, and it will then run. So that means that the threading engines for static and dynamic are quite different. And then for generative models, we've got a very complex multi-threaded environment to deal with the scalability. Let's say you have a local language model that you access, and you want it to do the work alongside everything else. You normally would need big infrastructure. Let's say there's a performance issue there and it takes a second or two to bring the result back. You can then decide if the threshold needs to go to Groq or some high-speed inference engine for outside feed. And you can then decide if the engine needs to do a feed-forward kind of approach. So that means that it caches or saves in it, and then gets loaded the very next time that the runtime gets called. So each approach, static, dynamic, and generative have got their own internal strategies, but for the person implementing it, you don't have to worry about any of what I've just said. All you have to know is that it's totally resilient. It never goes down. Resilient means that it is self-healing. It knows exactly what's going on. There are all kinds of checks happening.
No, thank you, Jen. That was a very detailed answer, and I'm happy that you linked all those points into how the threading takes place. That was a great point, especially because I was thinking you can also set that for the offer matrix. You can also change whether that's loaded statically or dynamically as well.
If you think about the typical data sets in recommender systems or interaction, science-related interactions, if you have dynamic offers, then all you want to get from your offer matrix that is a static scenario are the descriptions and the names. And what you want to do is load a dynamic that deals with the parameters of how dynamic, the threshold for where pricing gets set, because you always need pricing rules. Mm-hmm. Then you have a model that will score against not just a customer's demographic data, what the offer matrix has to offer, plus a dynamic threshold. It will then come back with a list of, let's say you do a propensity versus probabilistic scoring system. We'll bring back a list of propensities. You'll pick the ones, you'll go back, and all of that needs to happen. In our world, that normally happens in about 5 milliseconds. So that means that your entire execution path end to end, in a very slow case for us, is normally about 10 milliseconds. And in a very fast case, about 2 milliseconds. So it depends on the scenario. And if you do something like an entire wellness system, the turnaround time typically sits at about 70 milliseconds at the top end. If you look at like Vodabug or any one of those kind of calculations, normally take a bit longer because it has to do a lot of work on the execution path, dependencies, for you to get the person's immediate action, the money they've just spent, interaction they've just had on their phone, the transfer they've just done. You need to bring all of that into your dynamic pricing to then work it out and then update it before you pass it back to the user. So that means that there's, again, in a threading system, the perception of real time in some way.
That's actually a great segue, Jay, because something I wanted to show is I actually wanted to put a little bit of our money where our mouth is and check in the logs so we can push and score the spend personality predictor. This is a model trained to predict spend personality, and we're just going to use the test API from within the workbench to kind of validate, to make sure that your deployments that you've pushed to your different runtimes are actually kind of operational.
I had this question sometimes from people saying, well, I'm a bank and somebody needs to get a score. They can get it seconds or minutes later. And I say, well, absolutely. But now imagine the options that open up if you know you can do a whole string of complex scoring, related use cases and still get it done in less than a second. So let's say a person is about to sign into an app. By the time they sign in, if you look at telco client, you run between 12 and 15 use cases, and it loads entirely in about 80, 90 milliseconds. It means that you have all the options around how you engage in your user interface, what messaging you use, and you can then calculate the sentimental equilibrium to know what kind of messaging you're going to give the person. And as soon as you have that time to your disposal, your options explode, because now you can spend it on so many other things. You can build intelligent capabilities all over your entire digital journey, rather than just having to wait for this big thing to happen every few seconds or every few minutes. Maybe this is
personalization at scale, so to speak.
Yes.
Yeah, anyways, let's so we're just going to call this API a few times. So as we can see, I think this model's a bit overfitted. Just getting back a prediction from this, I think it's a gradient boosting machine. We can come check here if we want. Yeah, it's a gradient boosting machine that is meant to predict a customer spend personality. And now we can hop in the logs and see how long the scoring actually was. Here we can see execution time in milliseconds to get the final result was about 4.8 milliseconds to score against the spend personality model, prepare the final result, and send it back.
The point to make is that included in that time and the execution threading, to go back to Tadi's question, was that the backend threading engine deals with the logging responses and real-time convergence. All happens in parallel threads because it's not on the execution part. So the model scoring, getting the result back, and then when you call the API, you want within the next, let's say 50, 60 milliseconds, all the updates to have been completed so that you can have real-time convergence too, not just real-time scoring. And that's why you get that kind of performance. The kernel is designed to deal with this execution path priority, and all the other threads that are needed to make a scoring engine for real-time to work is already pre-built into the core architecture.
But importantly, all that logging and everything still sits, although it's happening in parallel, it still sits at a much lower priority than the main scoring threads you were talking about.
Yes. Like Grafana, it shows up within a few milliseconds. The data point will be available so you can review it.
Anyway, that's something we definitely wanted to show. Thank you, Jay, for all that great technical insight. Maybe we can hop back over to the slides, Nicola. We did just want to show the scoring of one of the models.
Yeah, I think we can move on to this slightly more in depth, talk about our integration with open source technologies as well. Yeah, go for it.
Jay already touched on a couple of these points, but we just thought this was a cool slide to add. He already mentioned the myriad of things when you're operating at such an efficient level in that millisecond order of magnitude, your options explode. So here we just wanted to kind of to speak to that. We wanted to add just a mention of a couple of pieces of functionality that are like kind of exciting us right now in the real-time space at ecosystem. So Jay already mentioned Groq. So Groq, for those of you who don't know, is an open source version of Llama 3 that is specialized to, Nicola, I think you know the numbers, but it's how many tokens? It's like quite a large amount of tokens in quite a small amount of time.
300 to 500.
3,200 tokens per second.
It depends on the model size that you use, yeah.
Yeah. So we have been experimenting, Jay specifically, because it's really his wheelhouse and he has a lot of fun doing it, but experimenting with integrating Groq natural language processing in the post score of some of our deployments so that you can code your offers in completely personalized generative natural language at that final stage and hand that back all in sub a second. So that's something that is very exciting for us right now, and we're really interested to see where that can go in the future. It's a bit early days, regulations is tight and everything, but it's still, to be able to be achieving that is still like very, very fascinating for us. Shout out to Groq. Well, yeah, newest sort of Llama fine-tuned Llama 3 model. And then another thing which I've found myself doing a lot recently in my work is experimenting with intelligent routing, which Jay also touched on a little bit earlier, in regards to like when an incoming request is made to a specific runtime, the levels of intelligence that you can add at real time, like milliseconds level, the amount of intelligent logic you can add in terms of how that request is actually routed. And this enables you to get some requests, given some specific parameters handed with the request, to get them to a specific model that is going to be very specialized in dealing with that specific task. You can make your models more and more specialized and then route incoming requests to the exact perfect model depending on some logic. That's fun to play around with and is showing great promise in what Jay was talking about, where there's this whole universe of options at your disposal as an enterprise, as a firm, when you're implementing intelligent systems in this small period of time. So yeah, and then the last point harks back to what we're talking about in terms of the architecture, a completely self-contained environment delivering AI capabilities in real time. It's really what we're all about. This, I think,
I'll speak
on
about
this one.
So this is just a bit of a, yeah, and those of you who've been in these meetups have probably seen these slides before, but I'm going to go a little bit more in depth into what we're seeing here. But this is kind of like an example of if an app interface had our technology implemented in it. So the first screen you can see in the top left corner, there's no profile image, which means the customer isn't logged in. So what they'll see on the screen is generic view and styling, and also messaging style. In the second slide, you'll see that the user logged in, which means the algorithm now has access to historical information and information about the customer. So it knows what historical preferences were and knows the space in which it is meant to be experimenting. And it will start presenting some recommendations to see how the user reacts to them. And then the third slide, you can see that as the person is scrolling, you have these dynamic carousels of recommendations that change in real time based on what their action is, what they're clicking on, what they're responding to, where they're hovering longer as opposed to other parts of the interface. It will continue making recommendations and using what the customer does to inform the next recommendation. And this all happens in real time. It all happens within seconds of you scrolling through this interface, and is highly relevant in keeping people on a page and keeping them engaged. Yeah, so that's just a little visual example of what it would look like. We are nearing the end of the session. So if anyone has questions or points they wanted to talk to, now would be the time. Jay, anything from you still?
Lots, but I think we'll leave it for the next time.
Okay. Okay, great. Cool. This was a really fun session. Thank you guys.
Thank you guys. It's always nice when we get an excuse to speak about this sort of thing. So thank you so much to everyone who did come and sort of lending us your ears. We hope at least you taking away one sort of interesting or exciting thing in this space, at least to think about, if not to act on in the coming days until our next meetup next week. Stay tuned. Thank you so much, guys.